Okay, class. Now we want to look at a example. What is not a subspace? Okay. What is not a subspace? From the previous example, we have just the set here, this H right there. And from the same set, if we now restrict the A and B are only non-negative, meaning A, B are greater than or equal to 0. Now, this set, H still passes the first and second requirement, meaning 0 still belong there and still close under addition. However, it will not pass the third requirement, meaning you multiply by any constant. Now we use the constant negative 2. Remember, A's and B are greater than or equal to 0. Now you multiply by negative 2, a constant scalar. Now the result of that is negative 2a. Since a is greater than or equal to 0, then negative 2a is less than or equal to 0. Negative 2c, no, b, is less than or equal to 0. That does not belong to H anymore because H only consists of the first and last element of greater than or equal to 0. So this is 0. So H is not a subspace. So you have to pass all three requirements in order to be a subspace. So now let's look at that. So property A, B, and C. Property A is 0, belong to this set. Property B is closed under additions. Property C is closed under scalar multiplications. Guarantee that a subspace is itself a vector space. So under the vector space operation already defined in H, meaning the addition and multiplication. So every subspace is a vector space. Well, conversely, every vector space itself is a subspace. All right. So now we want to talk about a subspace spanned by the set. All right, the set consists only of the 0 vector in a vector space is the subspace of itself. So it's called a 0 subspace written by this. And let's recall what's a linear combination of any sum of a scalar multiple of vectors, which is mean the span of V1 to Vp. Span V1 Vp meaning consists of all possible linear combinations of V1 to Vp. So, but definition, right? So any vector space in a V, which is the span of that, is some kind of linear combination of from V1 to Vp, which C1 to Cp are constants. All right, let's look at an example here. All right, given V1 and V2 in a vector space V, all right, let H be a subset, which is called span, meaning H is a subspace, is a subset of all possible linear combination of V1 and V2. Okay, we want to show that actually the span V1 V2 is a subspace. Okay, span V1 V2 is a subspace. So that's just every element in this span V1 V2, which is H, can be written as some kind of linear combination of V1 and V2. All right, so we want to check three things, right? Check whether 0 belongs there or not. Well, if you simply pick C1 to 0, C2 to 0, then you get a 0. Therefore, 0 is a subset of, is element of H. Second, we want to check whether it is closed under addition. Let's take a look. All right, let's pick two random element from H. Like U equal to S1 V1, S2 V2, and T equal to T1 V1, T2 V2. Well, we'll add them together following the additional rule. Then you add it together. You simply collect the like terms. You collect all the V1 together, you collect V2 together. The coefficient of V1 will be S1 plus T1. Coefficient of V2 will be S2 plus V2. Well, these two are real numbers. Therefore, the result is a linear combination of V1 and V2. Therefore, the result belongs to what? To H, with the span of V1, V2. Well, so U plus W is in H. Let's check whether it's closed under scalar multiplication. Well, we'll simply pick a random element S1 V1, S2 V2, multiply it by a C. Well, as a result, you follow the multiplication rule. Then we can group the C1, CC S1 together, CS2 together. Well, that's a linear combination of V1 V2. Therefore, it's an element of H. So H is closed under scalar multiplication. As a result, you satisfy all three requirements for being a subspace. So H is a subspace of V.